Hello and welcome. Today we're going to be talking about introducing the Lagrange multipliers method. And it's a method for optimizing multivariate problems under constraints. And that constraint part is actually very critical. Because of course most optimization is subject to some sort of constraint. When you're talking about an application. And for one example, of course, would be that you have a budget. Okay, you might want to maximize profit, but you have maybe a limited marketing budget. Okay, you can think of many other examples of how to maximize profit or maximize something subject to some constraint, maybe a limited amount of material and you have to maximize volume or area or something in a geometric context. All of those things can play a role. We've seen these problems before. So in a typical Calc 1 course, we've seen these sort of problems before, and they always have two ingredients. One, what we call is the objective function. And typically, you can write them as z is equal to f of x comma y. This is going to be a multivariate function. Okay, so that's a multivariate function. And the second thing we can talk about, beside the objective function, is that constraint. Okay, and that's usually set up as a g of x comma y is equal to c. That's some sort of constant. Okay, so of course in a Calc 1 course, you don't use multivariate calculus to solve. Instead, the type of problem can be reduced to just one independent variable. But now that you're in Calc 2 or 3, depending on which type of course you're taking at your specific institution, we can now look at, we can actually view this problem with multivariate calc tools. And we can have a much more comprehensive solution. Okay, so with that in place, let's now go through an example of a problem. So this is like a Calc 1, what I would call classic problem. Okay, so the classic problem involves a river, and you have some fencing. And this is your pasture. All right, and so you have choices. You have a y and an x there. So x, of course, is going to be the width, and y is going to be the depth of the pasture. Okay, and it's also subject to a budget. So the budget is, of course, we have some fixed amount of fence. Okay, we have that budget, okay. And of course our goal, if you're a cowboy or a cowgirl, one of your big goals, of course, is to maximize area of the pasture. And the one key thing here is that the river is a natural boundary. A natural boundary that you don't need to put a fence on. There. Okay, so of course your cows can go there. And of course, by maximizing area, you get more grass for your cows to feed on and whatnot. Okay, so again, this is a very straightforward example. So our objective function, that's going to be z. That's going to be our area. The objective function, that's number 1, is going to be f of x comma y. It's going to be very simple. It's just going to be x times y. Okay, cool. 2. The second thing you have is that budget equation, or what we call the constraint. Okay, and that's going to be g of x comma y is equal to some fixed number, we'll call it c, and that's going to, of course, be equal to x plus 2y, okay, because we have here 2 sides that are of y length, and then we have 1 width that we have to deal with. So in this specific case, I'm going to say that we have 1,000 meters of fence. Okay, well, you can pick any number you want there, any positive number you want. We'll go with 1,000 meters. Okay, so how would you solve? Well, it's pretty straightforward. What you have to do, of course, is find y in terms of x. So in this case, it's pretty easy. You're going to have 1,000 minus y, or sorry, oops, what I mean, 1,000 minus x is equal to 2y. So y is going to be equal to 500 minus x over 2. Right, that's always the first step here. Find y in terms of x. And then what you do is, of course, plug in to the objective function. So we have z, give ourselves a little bit more room here. Z is equal to x times y. We can now write that as x times 500 minus x over 2. And then, of course, what we do is we find the max. Is going to be found by taking dz dx. Let me write that a little clearer for you. dz dx is equal to 500 minus x, okay? And that's just taking the derivative of this thing over there. And then, of course, we set it equal to 0. We get x is equal to 500. Okay, very good. So that becomes what I call x star. And, of course, y, if you plug it in, if you plug this number in over there, you get y is equal to 250. Okay, so what you have is a rectangle. A 2-to-1 ratio rectangle is the optimal fence pasture in that particular case. All right, that was all great. You could use calculus 1 methods to do it, but it all boiled down to this. You had to be able to find y in terms of x. Okay, so it turns out this is not always possible. Okay, in this case it was possible, but it's not always possible to find y in terms of x. All right, so now in order to do this, now we're going to do a more general approach to figure this out. We're going to do a more general approach where we try to figure out how to come up with a more general approach to solve these problems in cases where it's not possible to do this substitution method and turn it into a one-dimensional problem where we just take one derivative and set it equal to 0. Okay, so let's try this more general approach. So the most general approach is, of course, we have that constraint. So it's g of x comma y is equal to c. Okay, we know that this equation, it defines a level curve. Okay, so if I have x here and y there, that could be a level curve defined in that way. We also have one other thing, that we know that if I take the gradient of f, this is always, of course, perpendicular to level curves. So level curves are always perpendicular. So what we can say is at every point, that's grad f. Every point on our level curve, the gradient looks like this. The gradient of g looks like this. Okay, so it could also be on the other side of the curve. It doesn't really matter. What matters, of course, is that these are all 90 degrees to the tangent vector of that level curve. And you can, of course, see a prior video about this. And you can actually understand why that will always be true. Okay, so we know this fact. That's a really important fact that we have here, that that the gradient of g is always going to be perpendicular to the level curves. Okay, so one more fact. Okay, of course, our goal here. So another fact, but before we get to goals, what we want to do, of course, is that, okay, our goal is to find a maximum or min, so what we call a critical point, of a different function, z is equal to f of x comma y, right? But we only consider points on the level curve. G of x comma y is equal to c. All right, so while we're on this level curve, we can investigate what z is. Okay, so of course, if I'm at this point, maybe z is equal to 1. And here, let's say z is equal to 2. And maybe it's 3 here. And then it's 4. And then 5. And maybe that's 4 again. And that's 3. And that's 2. And that's 1. And that's 2. And then that's 3 there. Okay. So again, this is a very simple thing here. The idea is that we could kind of monitor what z's values are. We see there's some points where it's quite high. So of course we have a specific point here at 5. That seems to be a maximum. Of course there could be other points in between there that are higher, but let's just go with this simple example now. We of course can also find points there where we have minima, okay? So the idea is what's going to go happen here. So what we want to do now is examine grad f, all right, along the curve, the level curve, defined by g of x comma y is equal to c. All right, so we want to know what's direction this point. So the question we have is, what direction does grad f point along the curve? So we find out here that, suppose I start here at z equals 2, and I find out the gradient points this way, and that's because I know that if I go along this curve, it should be pointing closer to where 3 is, because we should be increasing as we go in that direction. And let's say we have the gradient there, again, so this is my grad f, and that's my grad f, we'll write those in red, is like that. And then again, grad f is pointing up there at 4. But it turns out something weird happens. When you get to this maximum point, so again, I'm going to say that 5 actually is our maximum. Well, if I'm at the maximum, the gradient shouldn't point in any direction that's going to be along the curve, because the gradient always points in the most uphill direction. So we expect there the gradient should actually be pointing collinear with grad G. So at critical points, and that what we're talking about is max and minima, grad F won't have a component that's tangent to the level curve. Instead, we find is grad F must be collinear with grad G. What that means, of course, is that grad G is proportional to grad F by some constant. So we're going to have some constant that makes these proportional, right? So, for example, it could be that grad G at a certain point is equal to 1, 2. What we'll find here is that grad F will, at the same point, will be 2, 4. Or another one that could happen is grad F is equal to -3, -6, okay? So here in this particular case, lambda would be equal to 2, and this one, lambda would be equal to -3. Okay? So again, these are just examples to give you an idea. Right? So away from these points, if I keep going, my gradient should point in that direction more. And then we get to this minimum, and grad F should be there. And there again, you see that collinearity if this is really truly the minimum point. So collinearity means that they could be pointing in 180-degree opposite directions. Doesn't matter. That's still collinear in our sense of things, okay? And then, of course, we do this again away as we go away. Okay. So let's go to the next page. So what we discovered is that at max and min points of z is equal to f of x comma y along a level curve, g of x comma y is equal to c, grad g must equal lambda grad f. So this is a system of equations. So let's actually erase that. I'm going to erase this for a second and rewrite that. This is going to be grad g x comma y is equal to lambda grad f x comma y. And that's going to be a system of equations in terms of x and y, in terms of x and y, and with a constant lambda, which we'll discover when solving for x and y. Okay? So this system of equations, when solved, will produce those critical points. Okay, those critical points, which we're going to call x star and y star, like we did before. Okay. So lambda, again, can be a lot of different values. We don't know exactly what value it is, but we can discover what its possible values can be in the process of this. So Lagrange multipliers. Lagrange multiplier, when we say that term, what we're really meaning is lambda. That is our Lagrange multiplier, okay? And what we find is we need to discover what that number is. All right, so let's go through and actually solve it. Let's go back to our fencing problem. Let's go back to our fencing problem. Again, we had f of x comma y is equal to x times y. And our constraint problem was equal to 2y plus x is equal to 1,000. Okay, so what we'll do is we'll take grad f. So we take the partial derivative with respect to x, which is going to be y, and the partial derivative with respect to y is x. Okay, cool. And then the gradient vector with respect to g, if we take the partial derivative with respect to x, we get 1. And the partial derivative with respect to y is 2. Okay, so now we set up the Lagrange multiplier equation. And it's going to be y comma x is equal to, times lambda is equal to 1 comma 2. Right, again, right here we have two equations. Two equations here. So what we can do is actually break them out into those two pieces. What we really have is lambda times y is equal to 1. And lambda times x is equal to 2. Okay, so now we have to solve both. So we want to solve both of these equations. So let's see if we can find, so what we solve both and find x, y combinations that work for a particular lambda value. Okay. So we can figure this one out. So let's see if we can sort this one out. What we have here is y is equal to 1 over lambda, whatever that is. Okay. And then anywhere, and so we can do that. And then now, whatever that is, let's undo this actually. Let's go back. There's lots of ways we can approach this, but one way to approach this is we know that lambda y is equal to 1. So one thing we can do is actually say 2 lambda y is equal to 2. And we know that is equal to lambda x. So that means lambda times 2y is equal to lambda x. So actually lambda can be anything in this particular case, in which case what we get is 2y is equal to x. All right, so now we have to go look at the constraint. So we have to plug this into the constraint, and the constraint equation, of course, is all right, so we have that. And now, anywhere I see an x, I can actually put 2y in its place. So what we have here is 2y plus 2y is equal to 1,000. So that's going to be 4y is equal to 1,000. And that means y is equal to 250. And we can call that y star, and we knew that was the same values we had before. And of course, we know that x is equal to 2y. So that now means that x is equal to 2 times 250. Otherwise called 500. So x star is equal to 500. All right, so we found the same critical points as before. Okay, so of course this was a very simple example. Okay, in other videos, in next videos, we'll go over increasingly more elaborate problems. Okay, but this video, of course, we got the conceptual approach, why Lagrange multipliers works, and we applied it to a very specific problem, and we solved it 2 different ways to show that they do really truly give you the same answer both ways. Okay, so without further ado, I'll let this video go, and I'll see you on the next video.